Let's start then. Okay, so welcome everyone to TCS Plus, and today we have Muli Safra, and the operator for today's talk is Aded Regev, and behind the scenes as usual, we have Thomas Videk, Thomas Hollenstein, G. Kamat, and Clement Canon. Now, Aded will go around the table and introduce the groups.
Okay, let's hope I don't mess it up. So yeah, we have lots of groups joining today. Adam Smith, let me show you. Hi, Adam Smith and the group from Penn State. Hi guys. Oh, Sean. Hi Sean. And we have G. Kamat with the group from MIT. Hi guys. And Lila Fontes with the group from Paris. Hey. And we have Muthurama Krishnan joining us with the group from Rochester. Yeah, well, we don't really see you. It looks like you're behind a big cloud, but I mean, we see something. We have Sam Hopkins from Cornell. Hi, Sam. Thanks for joining. We have Shavastra with the group from MIT. We have Shrikant joining us. And hi, hello everyone. And the group from Simons Institute, Berkeley, that's joining us there. Okay, I think that, did I miss anyone? Oh, maybe I missed Thomas Vidik, yeah, with the group from Caltech. Okay, that's all. So back to you, Anindya.
Thanks, Aded. So, okay, sorry, why am I presenting to everyone? So I should stop this. Okay, so we have an exciting sequence of speakers lined up. 2 weeks from now, we have Elias Diakonikolas. Then we have Aaron Pottichin 2 weeks from then, and then Aaron Roth. Sorry, I messed up the schedule. So we have Aaron Pottichin. Then okay, that's the right schedule. Sorry, and after that. Okay, sorry, let me get my thoughts together. So during the talk, the audience shall be muted. If you have questions, you should unmute yourself and ask questions. And we encourage you to ask lots of questions. And again, today's speaker is Muli Safra. So Muli did his PhD from Weizmann. His earliest breakthrough result was in automata theory. And then we all know he did some breakthrough work in PCPs and hardness of approximation, and including the best known results for vertex cover, which is an amazing piece of work, a technical tour de force. Today he's going to talk about optimal testers for Boolean monotonicity. So Muli, you can start.
Edith, thank you, and I hope you all hear me well without too much echo. You do?
We understand,
okay.
Yeah.
So let me start. Okay, so this is monotonicity testing. We'll show some related work, which is the most technical part of this work here, is the isoperimetric type theorem of the Boolean cube. And this is joined with Subhash Kot. Dor Minzer, who's a student here and unfortunately is a bit sick, so this is why he's not joining us. If you will, that's, I hope you'll see him. And let's start. Okay, so property testing. What is property testing? I'm sure you all know. We have some universe, say graphs, function, or any other mathematical object that you're interested in. And we define a subset of it. P, the subset P, is all the objects that satisfy the property. And then we would like to very efficiently look at very few places on the representation of the object and be able to accept all the objects that satisfy this property, either with a high probability or, in the case of one-sided tester, with probability 1. At the same time, reject if the object is very far from satisfying the property. So epsilon is the parameter of how far we would like it to be in order for the tester to have to be, so it must reject. Distance can be defined in many ways, but usually it is defined as Hamming distance, so it's a number of bits in the representation that one needs to change in order to make the object satisfy the property. That I'm sure all know. Now, monotonicity testing was also studied in many different different object, but we'll today look at Boolean functions, the multiplicity of Boolean functions. So our universe is all Boolean function. What is a Boolean function? Boolean function gets n variables, n binary variables, and return a binary value. This is how it is defined. And this defines a partial order over all the inputs. So we say that x is smaller than y for all indices I for which xi is equal 1, yi must be equal 1 as well, but there may be some indices in which xi is 0, but yi is 1, then we say that x is smaller than y. That's a partial order over all the possible inputs. And if we define P to be monotonicity, a function that's monotone, which this is the exact definition, for every x smaller than y, it must be the case that f of x is smaller or equal to f of y. This is a property that we're interested in, and the distance we measure by the usual Hamming distance. We define this parameter, this important parameter that will keep appearing here. It's the epsilon of f is the distance of f from a monotone function, and the way we do it, we use the fractional Hamming distance, normalized Hamming distance. So it's the fraction of bits that differ from that you have to change in f in order to make it monotone. So I hope this is all clear, and if not, please do ask me questions all the time, whenever you can. Okay, so let's see what happened with this problem. It was first introduced in the seminal paper of GGLRS. I try not to mention all the name here. I hope people will not take it personally. This was introduced in '98. It's really a seminal paper introducing quite a few interesting problems in testing, property testing. And what they did is show that the number of queries you need to make in order to be able to test monotonicity is linear. That was also not at all trivial. We'll mention this proof a couple of times. So it turned out that you have to use a linear number of queries in order to test monotonicity. Is that the best you can do? Maybe you can do better. So another paper by Fisher et al. A couple of years later showed that this is in fact a good lower bound of square root of n. We'll actually look at it a little in a minute. And then it makes sense that we have square root of n lower bound, we have linear upper bound, and the big question was whether we can improve the upper bound, or maybe there's a lower bound, a linear lower bound. We tried to throw almost any technique that was around to solve this problem, but nothing worked until a couple of years ago, when a beautiful paper by Charobatri and Shadri showed a better than linear algorithm. And the proof is quite complex. We'll actually mention it also in this presentation. And what they showed is that you can actually do n to the 7/8 queries. And this was improved recently to n to the 5/6. What we luckily been able to show here, and this is what we'll present, is a tight algorithm showing square root of n number of queries to test monotonicity. I'll show the exact parameters. There's something to point here. The testers that we'll show here, these algorithms, will all be pair tester. I'll define it precisely in a minute, but this means that you actually only look at two inputs and decide whether to reject or accept the function. This is very limited. However, what we can do always is just repeat it as many times as necessary in order to get whatever probability of rejection you would like. So this is not only true for the testers that we'll see here, but all the testers that were suggested so far. And in fact, all of them are non-adaptive, so this means that they don't actually, they decide ahead on all the queries that they're going to make and only make the queries. They don't change the query that they make according to the value they got previously. Okay, here I am. Okay. So here is what is a one-sided pair tester. You pick x and y such that there's an order between them. X is smaller than y. And then you query f on x and f on y. And if you found non-monotonicity, you reject the functions. What does it mean, non-monotonicity? it means that f of x equals 1 and f of y equals 0. That's the only non-motolicity we can find between a pair of points if they are ordered this way, x is smaller than 1. Okay, and a one-sided non-adaptive pair tester will be such that if f is monotone, it will be accepted with probability 1. If f is far from monotone, epsilon far from monotone, epsilon f is larger than epsilon, then it should react with high probability. We'll say shortly what does it mean, high probability. Okay, so I hope this is all clear so far. And just a note, if the tester is one-sided, it must be the case that it only rejects the function if it actually found non-motolicity. Otherwise, you can take a monotone function and change it in only one point, and it will reject a function that will accept the function that you don't want. Okay, so here is the first tester, the tester of GGLRS. This is what we call the edge tester. It will become clear, I hope, later why it's edge tester. You just pick a random input x, and then a random index I. You look at x, and then you flip the ith coordinate of x. You get two inputs. You look at the two inputs. They are obviously ordered. One of them is above the other. And you reject if non-motolicity is detected. That's a simple tester. We'll see in a minute. We actually know that all of the inputs 0, 1 to the n are actually form the hypercube. So this means that we're actually looking at the edge of the hypercube, which is randomly an edge of the hypercube. And if it turns out to be non-monotone, this is the case in which we reject the function. Now, what will be the probability of rejection of this? Well, not at all trivially, but what GGLRS showed, that the detection probability of the edge tester is at least epsilon f, the distance of f from monotone, divided by n. This is a pair tester, and therefore, if you want to get constant probability of error, you just take the inverse of that, and this is number of queries. If you do that many times, then the probability of rejection would be 1 over e. Then you can just repeat it a few more times. Okay, so this is the tester from 98. It's a very interesting tester, and also the technique there are very interesting, beautiful results. Okay, let's see what we're going to do in the next few slides. First, I'll show you a lower bound of square root of n. It may be a bit technical, but I hope it will help us in the next few slides to understand what's going on here. Then we'll introduce a very interesting example. Let me say already now, I've been working at this on and off on this problem for, say, at least 10 years. And for the last 9 years, I've been working on conjectures that were simply not true. And this example, it's a relatively simple example, show why it is not true. And this is what we'll show this example. And I hope that it will make clear why we have to change the tester and make some particular choices in the tester. And then we'll be ready for the analysis of the tester. Again, I hope everything is clear. If not, then just let me know.
Muli, is it easy to see why you need at least n queries for the edge tester?
Well, let's see, easy. Yes. Well, actually, we'll see. I think we'll see it in an example. It'll be clear then. I'm not sure it's easy, but the example, the tiebreaker example, I think will show also that.
Okay, thanks.
If not, then just follow me again. Okay, so this is, well, I think the best way to look at the hypercube and also certainly all the inputs. We have 2 to the n inputs. 0 to the n will be here at the bottom. 1 to the n will be here at the top. And if we look at this, all of these inputs, and we consider monotonicity, almost all of the inputs are within this middle section here, containing all the inputs in which the number of ones is roughly n over 2. So it can deviate by some constant times square root of n, the number of ones. So this will describe this section here. And you have 1 at the top but 0 at the bottom, but since these two parts, by simple Chernoff bound, are negligible, you can just assume that this is the value of the function. It will never make a function not monotone if we decide to do that. So let's go ahead and decide that all our functions are like that, and therefore it doesn't make sense to even query the function in there because the values are already set. So now the question, remaining question is, what do we do in the middle section? So what do we do? This is, again, I remind you, this is an example. We want to show that the pair tester cannot detect non-monotonicity in a function with probability higher than 1 over square root of n, or some constant times square root of n. What we do is we put a random anti-dictator in the middle section here. What does it mean to be an anti-dictator? We just set, as I said, 1 at the top, 0 at the bottom. And in the middle section here, we choose a random I, and we took whatever xi is telling us, whatever the value of xi, and we just flip it, and this will be the value of the function f. This is story-wise. You don't know what you have 2 restaurants, and you don't know which one to go to. So what do? You pick someone who's you don't trust. You ask them where to go, and then you go to the other restaurant. Okay. I hope this now makes better sense.
Now it's totally clear, yeah.
Right. Okay, now let's assume that we are looking at a non-adaptive pair tester, and it's trying to actually identify this function and figure out that this function is very far from monotone, and we want to see what is the probability for a pair tester to detect that. So notice that the pair tester must look at 2 inputs. X is smaller than Y. Since we made these 2 parts trivial, then it must ask some questions here, and the distance between the bottom part here and the top part here is some constant times square root of n. Therefore, the distance between x and y, the number of indices on which they differ, on which xi is 0 and yi is 1, is at most some constant times square root of n. What is the probability that the randomly chosen I will be in that set? It's 1 over square root of n. So if it just so happened that the indices that are the difference between x and y happen to contain this I, this is the only case in which this pair tester is going to reject this anti-dictator, the random anti-dictator. Okay, this was rather technical. I hope everyone is clear about that.
That, by the way, also answers my question. You need the edge tester will need n queries to see that.
Exactly right. You're right. Excellent. Yeah. The number of edges, the fraction of edges here that are negatively influential is 1 over yeah, it's like constant over. Excellent. So I hope this is clear. This is important trial. Okay, so here is the new suggestion for a tester. Let's do the following simplistic extension of what we had before. What we'll do is we just pick randomly 2 inputs, x and y, so that our order, so x is smaller than y, so that the distance between them is exactly square root of n, maybe roughly square root of n. We'll pre both points, and then if non-monotonicity is detected, we'll reject the function. Very simplistic extension of the tester. And you would think that this will actually give you a good probability of rejection, right? This is what I thought, at least, for 9 of the last 10 years. So here is the tester we suggest. Pick 2 random points so that the distance between them is square root of n. Just query both of them and reject if non-monotonicity is detected. It seems that this will multiply the probability of rejection of any function by square root of n, because the distance here is square root of n, and then we'll get the perfect tester when we match the upper bound, the lower bound, sorry. We'll get the upper bound that matches the lower bound. Point is that this is completely wrong, and here is a simple example. I hope you'll see that it's simple, that actually shows that this is not the case. Here is the tiebreaker function. We're choosing, say randomly, but it doesn't matter much, some k variables of the n variables. And we look at them. So we actually apply majority to these variables. So if the number of ones is smaller than k over 2 on these variables here, then the function is evaluated to 0. If the number is more than k over 2, then the function is 1. And now the only remaining case is what happens when you have equal number of ones and zeros. So it's exactly k over 2. Since k is even, let's assume that k is even, this could happen and this is not really defined. So what do you do then? Let's just go back to our story. Suppose you're actually trying to decide on out of 2 restaurants, and you can't decide, so you take a majority. But what happens if there's no clear majority, if it's exactly half and half? Again, you go to this guy whose opinion you don't trust, and then you flip whatever values they tell you, and you go over there. Just to make it clear that this is story, it's not, the last time Oded hosted me and gave me some of his baking goods, and it was excellent. So this is not really to do anything. Just I had a story, and I had to find a matching place to them, and this is what I did. In fact, I suggested for the next meeting of the TCS Plus, Oded will bring some of his baking. Maybe we can spread it around. Okay, so you see, this is a function. I hope this is clear. Forget about my funny stories. You just take majority over k variables. K is even, and therefore it's well defined, except for the case where k, the number of ones is exactly half on this case. And then you take the anti-dictatorship on one random variable of the rest of the variables. Right? This is a simple example, I think, simple function. Rather simple function. I hope I knew about this function much before. Now let's see what happened with this function when you try to actually detect this. So in order to detect non-monotonicity, it must be the case that both the points that you've selected are in the middle layer here, where the number of ones on the k variable is exactly k over 2. Because if one of the points is below there, then you obviously get 0, and there's no way to detect non-monotonicity. If one of the points is also on the top part, where you always get 1, then again, you don't get any non-monotonicity. So the only way you can get non-monotonicity if both of the points are in the middle layer here, where the number of points is exactly k over 2. And now, this means that the distance between them must be not much larger than n over k. Because you take the input x, and then you randomly choose n over k indices in which x is 0, xi is 0, and you flip them to make them 1. If you choose more than n over k, then it's very unlikely that you didn't actually touch one of the variables in the k variables here, and then immediately you go to the top part, and the value of the function is trivially 1, and you will never detect any non-monotonicity. Okay, this is not so trivial, so let me know if you followed me, and if not, please ask some questions.
So can you say again, so what is the conclusion? Okay, so we have this function, but then what?
So the conclusion so far is that the distance between those 2 points that the pair tester make must be not much larger than n over k, whatever k we choose. So,
well, the distance to monotonicity of this function is not so big. It's 1 over square root k.
Right. So actually, let's look at parameters. If the example was clear, then the parameters are, suppose let's set k to be n over 2. And then this means that the distance between the 2 endpoints must be constant. So this actually means that the edge tester is actually doing the best you can on this function. And in fact, this shows you that if you want the denominator here of the probability of projection to be n, then what you must have here is the epsilon of f, the distance of f from monotone. And if you would have liked it to be square root of n, then you must have epsilon of f squared. And actually, if you look at this function and set k to be n to the 3/4, that neither the edge tester is doing very well, it's actually doing quite badly, nor the tester which picks 2 points that are of distance square root of n. They're all doing poorly. And let's see what the point is. The point is that you have some, in this function, you have some negative edges, some small fraction of them. But the point is that if you look at the negative edge, then immediately above it you see many positive edges that counter the effect of the negative edge. So if you take a long run on the cube, you're not likely to hit any non-monotonicity. Again, I'm not sure it's clear. That is clear. Somebody else? Should I say it again? Let's just pick it again. Suppose you just choose X. It's a random input. Suppose you were lucky and it actually falls within exactly the middle layer there, where the number of ones is exactly k over 2. This is the probability of that happening is 1 over square root of k. Now, suppose this happened. Now you look at a set of n over k bits where xi is 0 and flip them to 1, and hope that you didn't hit any of the k variables that form this majority here. If you only hit one of them, it'll be enough so that now you're in the section where the number of 1 is more than k over 2, and therefore the value of the function in 1 is 1, and you'll never detect any non-monotonicity. So it actually shows the distance between the point must be limited to n over k, otherwise you're very likely to hit one of these variables. And depending on k, this tells you that different distances are required in order to detect non-monotonicity. It's clear now, I hope?
Well, you introduced some dependence on epsilon. Before, I didn't care about epsilon. So if I don't care about epsilon, this is meaningless because I just, as far as I'm concerned, you can have some terrible dependence on epsilon. I only care about distance.
Okay. Maybe I think I see what your point. Suppose I actually put here some log n, not n over k, but n over k times log n. And then the probability of not hitting those variables will become very small, much smaller than epsilon. That's the problem?
I'm not sure. I mean, I think I'm just trying to say that the distance of this function to monotonicity is very small. It's 1 over square root k. So I don't care about this function. It's basically already monotone.
No. Don't think of epsilon as a constant. In general, don't think of epsilon as a constant. It is not even the case that if you think of it as a constant, you get better results. But for the purpose of this analysis, epsilon is not constant. Epsilon could be very small, and we still like to come up with a tester that works as a function of what epsilon is. This is why you put epsilon into the parameters here. Otherwise, we could just ignore them and say that it's a constant. So epsilon could very well be 1 over square root of n. That's fine. We still would like to get some good tester for functions that are so close to monotone.
But you allow the query complexity to depend on epsilon, right? So if epsilon is like very small, let's say 1 over root n, then having a query complexity of n over epsilon square is not a big deal.
Yes, but look, I'm concentrating here, and this is not, I can generalize it, but not time in this talk, but on pair tester. So I only query 2 points, and the question is, what is the probability that I detected non-monotonicity? So I would like it to be, eventually, we'll show that it's epsilon squared over n, epsilon of f squared over square root of n. This is my goal. But this is a probability of detection. I still stick to the pair tester where I only look at 2 points and just care about what is the probability of detecting an error. Okay, you see that the probability will become very small if I go beyond n over k. Maybe n over k could still be a constant, but if I go a little bit above that, it immediately become very, very small. Suppose I take n times log n over k. The probability that I didn't hit any of the variables, the k variables here, becomes very, very small. Okay? Or then are you fine with this?
Yes.
Okay, great. So this is a great example. It shows us that we actually need to look at very different distances for very different functions, and how would you do that? So let's deviate for a minute before that. GGLRS, what they did, I already said it, but it's repeated. They show that in order to get a constant probability of rejection, you need to take n over epsilon queries. What these two guys did in a beautiful paper is n to the 7 over 8 divided by epsilon to 3/2. And Rocco and his students managed to prove recently n to the 5 over 6 divided by epsilon to the 4. And again, what we'll do here is show square root of n divided by epsilon squared. This will be the number of queries. What I will show you that I can get a pair tester with the inverse of that as a rejection probability, and therefore you should just repeat that many times to get a constant probability of error. And this is optimal up to logarithmic factor to the lower bound of Fisher et al. I will stop saying these logarithmic factors with you because they appear everywhere and it will take me too long. Okay, I hope this is clear. Going a bit slower than I expected, but this is expected. Okay, let's see what we do here. We actually change the tester, and this is the first interesting point. We pick a natural number between 0 and half log n. This will be described for us what is the distance that we're going to choose. Then we pick x to be random. Well, then we pick the probability half, we go up the hypercube, and probability half, we go down the hypercube, and the question is, what is the distance to the other point that we're going to test? And the distance is exactly 2 to the L. So L fixes for us the power of 2 that will actually determine what is the length distance of the other point to x. So we choose this set of indices s of all the i's. If we go up, we look at x's, i's in which xi equals 0. Then we flip them. And we look at the 2 points, so the distance between these 2 points is exactly 2 to the L. And we reject if the probability, if we detect any non-monotonicity. And this is a tester. Let me say it again. What we did is, another way to say it, it's a similar tester, but one that will work quite good, or similar, is that we actually decide to run all of these possible L's. There are only logarithmic, many of them. So if you don't care about logarithmic factor, we can just, instead of running a pair tester, we run a test that actually look at logarithmic number of points each time. We'll do the same test for every possible L. And there's not much difference between this tester and the tester I just described you on this slides. They will work quite the same, and then the magic is that we can later decide on which L to concentrate. This is what we'll do in the analysis later. Okay, and the theorem that we prove here is that the detection probability of this tester is larger than the distance of the function f from monotone divided by square root of n. As we said, this is rather optimal up to logarithmic factor. So this is what the aim of the rest of the talk is, to prove this, show you this bound on probability. Okay, let me just give you a roadmap to the proof and the rest of the presentation. We'll begin by introducing, for a given function f, a graph G minus. This is a graph of all the negative edges. I'll define it precisely in the next slide. And an event R, which is some scenarios in which the tester actually rejects the function. We would like to say that R, the probability of R is large enough. This will be suffice for our purposes. There'll be some issues with this event. We'll show it a bit later, persistency and overcounting. And for this purpose, we'll define a subgraph G prime, sorry. G prime will be a subgraph of G minus, a subgraph on edges and a subgraph on vertices. But G prime will satisfy some properties that will be very helpful for our purposes. It will be a bibyte graph, the same as G minus. It will be regular on one part, on the upper part, the U part. It will be regular. All of the degrees will be exactly D. It will be semi-regular on the lower part, so the degree will be bounded by at most twice D. And there will be some lower bound on the side of this graph, as we'll see. And then we'll try to estimate R prime and do the analysis in order to show that R prime is in fact large enough for our purposes. So that's, I hope this will help us see how the proof goes, and I'm not sure where should I stand here, because this is important. This is a test, the tester that we introduce. We choose L, and let me choose distance to the L. So I hope this helps you when you look at the slide here. Okay, so we obviously have the hypercube. The hypercube has all the vertices and all the inputs here, 0, 1 to the n. And all the edges are two inputs that differ on only one index, x and x, well, I is flipped. When you look at the Boolean function over the hypercube, it is labeling by 0 and 1 all the vertices of the graph. So this is some pictures that can demonstrate that. We have some of the vertices being 1, some of the vertices being 0. And then we have some edges. These are the edges of the hypercube. So these two inputs differ only one index. And I color here the edges according to what they do. So you look at this edge, the black edges. They are non-influential edges. The value at the two ends of the edge is the same, 0 here and 0 here. It's 1 here and 1 here. We have some positive influential edges. These edges are where the value at the bottom is 0 and the value at the top is 1. And these are negative edges, negatively influential edges, where the value at the bottom is 1 and at the top is 0. So this is going against monotonicity. These are the important edges that we need to look at. These are the edges that the edge tester is looking for and rejects whenever it sees them. And the subgraph G minus will be the subgraph of the following. First, let us ignore all edges but the negative edges. So we'll just take them out, remove them. And then we are left with some isolated vertices. These are isolated vertices. They are not connected anymore in this graph. So we'll just remove them as well. And this is exactly the definition of G minus. So it's a graph of all negative edges. We ignore all other edges, and if some vertex become isolated, throw it out. Okay, this is important. This G minus graph is important for all the analysis, not only ours, but also previous analysis. So we've defined G minus, we need to define the event R, and this is what we'll do next. Here is the graph G minus. Now I've drawn many more vertices here. We'll call the bottom part, the one where the value is 1, the D part. This is for down. And the upper part is where the values are 0. The upper part, and obviously we got the bipartite graph. And now let us consider the following triplets, X, Y, and Z. This is a triplet that actually indicates some non-monotonicity detected by the tester. X, Y, and Z is an interesting triplet if X and Y are an edge in G minus, so this would be X and this would be Y. And on top of this, Z is above Y. Let's see what is the picture here. We have X that is here in the D part of the graph. We have Y, Z that is on the top here. And we want to say that there exists some Y here that is the neighbor of X in the graph G minus. And so that Z is above it according to the order defined on the hypercube. So this is the event R. The event R is that the tester has picked X and Z. If f of z is 0, then we have detected non-monotonicity, and this is the event that we are interested in. I hope this was clear. Tell me if not. Let me just recap that. We have triplet X, Y, and Z. X and Y are just an edge here, and Z is above the vertex Y, the top of the edge here. And we also require f of z to be 0. This will indicate that if the tester has picked X and Z, it has found and detected non-monotonicity. And obviously, this is a subset of the possible non-monotonicity detected by the tester. So here is precisely the event R. We have X and Z chosen. We restrict ourselves to the cases where X is chosen from D, from the bottom part of the graph. There could be some other non-monotonicity detected without this condition, but we restrict ourselves to this case. We want f of z to be 0, otherwise there will be non-monotonicity detected. And we want the order between them to be that y is between x and z. Okay? So let me know if this is clear.
It seems like you may be losing a lot by assuming that x is in D. You could potentially also take something below x.
Basically, but it's good enough. In some cases, we do lose, but we don't care about it because the value will be good enough. It's surprising. At first, you think that many of the normal monotonicity detected is not coming from this case, but in fact, it is. But note something very important. I said that we started X. This is the 2 points are X and Z. I didn't say anything about how do we choose a subset of points, of indices that leads us from X to Z. And there are many ways to choose them if you choose them according to some order. So if you think about as a walk along the hypercube, it doesn't necessarily have to go through Y. This is important analysis. Okay, so this is the event we're interested in. We like to actually lower bound this event. Here I just defined R now. So I hope R is clear. And next, we'll try to analyze this and show that the probability of R is lower bounded by epsilon f squared divided by square root of n. The squiggle here is actually hiding some logarithmic factor that I won't even say from now on. And the question is, how do you prove such a thing, right? How do you go about proving what would be the strategy to proving this? And here, why you'll see what is the strategy, and then you'll see why we are willing to forget some of the normal monotonicity detected in order to be able to analyze it better. So what we'll do is we'll charge all of the triplets xyz to the edge xy. See, we have an edge here in the graph G minus. It's an edge between x and y, and we'll charge them. All of the triplets where some z is chosen over there above y, we'll charge them to the edge xy. Hopefully this will work. Then we can just multiply by the number of edges in G minus and get a good bound, a good lower bound on the probability of detection of normal monotonicity. That's a good strategy. However, it has some problem which we'll mention in a minute. Okay, but I hope it's clear what is the strategy. This is why we want G minus to be as large as possible in terms of edges, and then we can just look at what is the probability of finding such a Z for a given X and Y, which is an edge here. That's obviously, there's two issues with this strategy. A, it could be the case that Y is very problematic. It could be the case that almost all the Z's above Y, as it turns out, the value that F gives them is not 0, but 1. Maybe there are many positive edges above Y, and the value changes very quickly. And it's the case that F of Z, with very high probability, is 1, and then we are not going to detect any normal monotonicity because F of Z equals 1, and then there's no normal monotonicity between X and Z. That's one problem. This is what we call persistency. And the other problem is that it could be the case that Z resides above more than one Y. It could be that there's Y1, which is the neighbor of X, and there's Y2, which is the neighbor of X, and Z is above both of them, and then it will be overcounting. So this is not a good idea to just count like that, because maybe we're overcounting. Some Z's appear for many different Y's, and this is will not be a good bound on the probability of detection, non-monotonicity. Okay. So this is clear so far? I hope the strategy is clear. We're going to count what's the probability of rejection we assume to have for each edge, and then multiply by the number of edges. But these obviously have two issues, two major issues that we need to resolve. Okay, so if that is clear, then here is the solution that we have found. We'll move to a subgraph of G minus, call it G prime. And both of these issues will be resolved by moving to this subgraph we will define in the next slide. Okay. What is a subgraph? The subgraph, as I said, we call it G prime. And this is a subgraph. So D prime is a subset of D for G minus. U prime is a subset of U. E prime is a subset of the edges of G minus. And we have another parameter, D, that's a degree. And the graph G prime is U prime regular. All of the vertices in U prime have the same degree in G prime. They're all of degree D, exactly D. There's also a good bound on the degree of the bottom part. All of the x's in D prime will have a degree of at most twice D. So it's not much higher than the degree at the upper part. And we also have some good lower bound on something which is similar to the size of the graph G prime. So if we set sigma to be the size of u prime divided by 2 to the n, this is the fractional size of u prime, then we say that sigma squared times d, the degree here, is lower bounded by epsilon squared, epsilon f squared. Let me try to make sense of this parameter here. If you look at sigma times d, it is in fact the number of edges divided by 2 to the n, because sigma is a fractional size of u prime, and d is a degree of u prime, so sigma times d divided by 2 to the n, multiplied by 2 to the n is exactly the number of edges we have here. And then we multiply it by sigma, which is the relative size of the set of vertices, and altogether this is bounded from below by epsilon f squared. This is a very crucial parameter, and the proof. This will be most of the technical part of the proof. So, in fact, most of the difficulty in the entire proof is proving this lemma. But I hope I can convince you shortly that assuming this lemma, we can actually get a good lower bound, good estimation of the probability of non-monotonicity detected by our tester. Okay, is it clear? Anybody? Oded? Okay. So assuming this lemma here, what we'll do is we'll look at R prime. R prime is just event R adjusted to the graph G prime. So we have X and Z, and X is now D prime, F of Z still has to be 0, and there exists Y, which is between X and Z, but now it's in G prime, not in G minus. And then we'll prove this probability of R prime being large enough, being epsilon squared over square root of n. You see that the epsilon squared will be coming from this part. And the proof is a bit surprising, but let's do the first step, and I hope you'll see the magic of the tester here. So what we'll do is we'll set tau. Tau will be the length, the distance of point that we are interested in. So we'll set tau to be sigma times square root of n divided by log n. Never mind the log n here. I don't have time to mention exactly why it is here. And tau, if you want to be precise, has to be a power of 2. So it takes a power of 2 that is close to this value here. And this is the distance that we look at. Remember, I said that the tester has, the tester has L, logarithmic number of choices, and I said that the magic is that we can think of it as if we have run all of them at the same time. And here is a bit of a magic. We look at the function f, we define G minus, then assume that we can find G prime. And only once we see G prime, this is only the time when we decide which distance to look at. So this is why we avoid the problems that come from the tiebreaker function, because we can decide on which distance to look at only after we've looked at the function and defined G prime for this function. Only then we decide on this. Okay, how do we find G prime? I don't have much time to say it, but we try all possible D's that are, again, a power of 2. So we try D, set D to n over 2. We try it. If it works, fine. If not, we look at D being n over 4, and then n over 8, and so on. And we can eliminate some of the edges to make the degree precise. And the proof will have to show that one of these values for D has to work and give us that G prime here. Okay, but we are assuming this lemma here, and we want to show that this lemma here resolves the two issues that we had before. So we've shown G prime. We've also defined what is R prime, and our next goal is to try to estimate R prime and show that these two issues are resolved. Okay, so we now take an aside. I don't have much problem, so I'll show you this and I'll jump ahead. But this is something I find kind of surprising, magical a bit. Probably most of you know what is the total influence of a function. It's a fraction of influential edges multiplied by n. We can divide it into negative influence, a fraction of negative influential edges multiplied by n, and the positive edges, the fraction of positive edges multiplied by n. And here is an interesting lemma. It could be the case that the number of negative edges and positive edges is roughly the same. This is what you would assume on a random function. But suppose you know that the fraction of negative edges is much smaller than the positive edges. Much smaller would be, like, say, half of the positive edges. If it's zero, if a fraction of negative edges is zero, this means that it's a monotone function. And then we have a very good bound on the total influence of the function. Among all monotone functions, the function with the most total influence is majority, and the total influence for majority is square root of n, so we have a good bound. We know that the fraction of influential edges for monotone function is 1 over square root of n. But now suppose we have a much weaker premise. We just know that the fraction of negative edges is, say, half the positive edges. It turns out that it's roughly the same. Have some different constant, but essentially the fraction of influential edges must then be at most 1 over square root of n. This is I find it kind of a magical statement. This is something quite surprising. And maybe more surprising is that the proof is a one-line proof. I can just leave it to you as an exercise. In fact, there are two one-line proofs that we know of, and it's very surprising. Now the question is, what do we do with that? The corollary is that in order to get the fraction of influential edges to be more than 1 over square root of n, it must be that they are almost the same. The negative and positive edges must be almost the same. How does it help us? Remember, we had this tiebreaker example, and we said that maybe whenever we have a negative edge, we have many positive edges above it. And this will actually ruin our probability of detecting non-monotonicity. Well, this lemma here tells us that it's not the case. So we can assume from now on that the total influence is smaller than square root of n, meaning that the fraction of influential edges is less than 1 over square root of n. Why can we do that? So first of all, observe that the edge tester is one of the testers that we look at. If L is set to be 0, then 2 to 0 is just 1, and then we are just looking at edges. And if the edge tester rejects the function with probability more than 1 over square root of n, then we're done. We have nothing to prove. This is the best that we can hope for. So we can assume from now on that the edge tester detection probability is smaller than 1 over square root of n. And now this lemma tells us that this actually bound the fraction of positive edges to be, again, 1 over square root of n, because either they are the same, and since the fraction of negative edges is smaller than 1 over square root of n, and they're the same, then it's also 1 over square root of n. And if they're not the same, say that positive edges is trying to be twice as many as the negative edges, this again will bound the fraction of positive edges to be 1 over square root of n. Okay, I hope this was clear. The bottom line is that we can assume from now on that the fraction of influential edges is smaller than 1 over square root of n. And how does this help us? Let's set y to be all the problematic vertices in U prime. Problematic y's are ones in which if you take a tau minus 1 walk up the hypercube, the probability of the value changing and not being 0 anymore, as it is in y, is more than a third. This would be problematic. All the other y's, we can assume pretty much that if you pick z above them, and the distance is tau minus 1, will be fine. So we try to limit, to bound from above, the fraction of y that are problematic in this way. So we set alpha to be that fraction, those that are not persistent after that. And then look at what happens here. Alpha is bound from above by this following. Each time we go up by one, say an edge up the hypercube, this bounds for us the probability of the edge being influential. We said that I over n is really the probability of influential edges. There's some differences between different layers of the hypercube, but these are really meaningless here. So we walk tau minus 1. I just wrote here tau instead. So this is limited by tau times the probability of each edge being influential. So it's tau times I over square root of n. Now we apply the setting that we set the distance tau to be. This is sigma times square root of n. So we replace tau by this here. And then the previous lemma tells us that if you have square root of n and the total influence is smaller than square root of n, divided by n, and this is smaller than 1, altogether telling us that the fraction of problematic y's is much smaller than the size of u prime. So even if all of these problematic y's will gain up on u prime, it will still be a small fraction of the vertices in u prime that will be problematic. And here comes the interesting property of G prime, that since it's regular on U prime, that this means also that the fraction of edges that will be problematic in this sense will be very small, and we can just ignore this case, this problem altogether. So this issue of non-persistency is resolved because of this lemma here, and the fact that we require U prime to be regular, and therefore we know that the fraction of edges that are problematic is negligible. Okay, this was, I hope, okay. It's a bit difficult, but I hope you followed me somehow. Any questions? Okay, I have a couple of minutes, so let me just say that we quickly go through it. Overcounting is actually quite easy. We can just assume that instead of inequality here, there's some equality, and then the probability of z being in any one of these, above any one of these y is small, some small constant, and then the probability of z being on top of 2 or more of these y's is very simple. It's very small. This is a simple calculation. It's an inclusion-exclusion principle, and this is done. You can follow it easily. Okay. And the point is that what we want to do is complete all this and show that what we have here is a type of isoperimetric type theorem. What is, okay, but just tell me, how much time do I have? I'm not sure I have much more time.
You can take 5 more minutes at least.
5 more minutes, yeah.
Okay, so let me try to do some justice to the main mathematically interesting lemma here. One can define the sensitivity of a function. This is sensitivity, the number of indices that when you change them, change the value of the function. We can also define the negative sensitivity, the number of indices that when you change them, change the value of the function against the monotonicity. And this is a very nice definition, the negative. Now, it is a well-known, a very simple inequality that the total influence bounds the variance of any Boolean function. This is a simple proof. And the interesting part is that you can actually put a parallel here. You can think of what GGLRS proved as a parallel for our purpose, what we call a directed parallel. Directed because we only look at the negative influence in one direction, not in the other direction. We replace the variance here by the distance of the function for monotone here, and replace the total influence by the negative total influence. And somehow this is what they managed to prove. You can think of what this beautiful paper of 2 years ago have done is to show a version of this inequality. What they said is that the negative total influence times the maximal matching in G minus is bounded from below by epsilon squared, and this is how they got the 7/8. And this could be parallel with Margulis inequality. It's a very nice inequality that says that the total influence of a Boolean function times the vertex boundary of the function, namely the fraction of vertices that are on the border. So you can change one index and change the value of the function. So the product of these two is bounded from below by the variance of the function squared. That's a very interesting inequality. And what's more interesting about this inequality, A, that it was written in Russian and nobody could read it, and B, that Talleyrand in '93 had a very nice generalization of this inequality. He just said, let's just actually take the sum of the square root here and the square root here, And this is what is the inequality that he got. So this is Talagrand's inequality. It says, we all know what is the expected sensitivity of the function, the average sensitivity, that's the total influence. And this bounded the variance, as we showed in the last slide. But what Talagrand says is that if you take the expected square root of sensitivity, this also bounds from above the variance of the function. This is very interesting inequality. And again, the proof is rather simple. The proof is, in fact, by induction. If I have 2 minutes, I could have shown you, described to you what is the proof. It's rather simple. And here's what we did here, which essentially seals the deal on this and proves the lemma that was necessary. What we said is, let's take the directed analog, parallel of this inequality here. What Talagrand did is take the expected square root of sensitivity, and we replaced it by the expected square root of the negative sensitivity in each point. And what he had here is the variance of the function, and we replaced it by the distance of the monotone. This is essentially the isoperimetric inequality that we have proven. The proof is much more complicated than Talagrand's because epsilon doesn't behave well. The distance of the function for monotone does not behave very well when you do an induction. But we managed to prove it, and one of the things we did, and I don't have time to show it, is actually replace epsilon, the distance from the function for monotone, by a different distance from monotone, and showed some interesting properties of it. But this is, if you want to, the message out of this is that this inequality is really the heart of our proof. It's really taking Talagrand's inequality, which we found illuminating, and transferring it to this world when you actually take the negative sensitivity instead of the sensitivity, and the distance from monotone instead of the variance of the function. And this is what let us do that. So as I said, the proof is very different. Epsilon doesn't behave well, and therefore we move to a different definition to monotone. Switching, I think I don't have time much anymore, so let me skip to the open questions. Switching is a very interesting technique called downward shift. This was used by GGLRS, in fact, to begin with, and the distance, we define distance according to epsilon and showed some interesting properties of this distance. There's another thing that we have to do in this proof is look at some split operator in order to seal the deal on this and move the function into what we call a pure function. In fact, it's unate functions, but no time for all this. So let me just skip to the end. And these are the open questions. So very recently, I think last December, the same group of guys actually showed a lower bound for the two-sided tester. We showed here the lower bound of square root of n for the one-sided. They showed the lower bound for the two-sided error tester. And this is quite not at all trivial. They have to do quite a lot. But this means now that not only but we have a tight bound for one-sided error, but we actually have the same for two-sided error. It doesn't actually help. On the other end, nothing is really known for adaptive tester. It could be the case, not that we know of any strategy, but it could really be the case that if you look at some values of the function and then decide accordingly what next to look at the function, you actually can get much better tester. In fact, the only lower bound that we know there is logarithmic. So this is very interesting still to bridge the gap between square root of n, which is the upper bound, and the trivial upper bound and the logarithmic lower bound for adaptive testers. And then another interesting question is we show you the parallel of the Talagrand inequality. And in the proof, for some reason, we got some dependency of the dimensions. There's some log n factor there that I didn't show you. And this is not the case with Talagrand. Talagrand managed to show a tight bound. And we actually don't know what the real value is. It could be the case that the log n factor there is necessary. And it could be the case that one can prove a different proof than ours, I guess, that will actually show that this logarithmic factor is not at all necessary, and you can actually get a tight bound the same as the telegrams, the parallel to telegrams. Okay, so let me end here. I hope you have some questions, and otherwise that it was rather clear.
Okay, thank you.
Thanks, Muli.
Any questions?
So I have a question. I have a question about the monotonicity, the last isoperimetry type theorem. So is it possible to have? I'm not even sure what the right theorem will be, but is it possible to have a continuous analog of these kind of isoperimetry, directed isoperimetric inequalities, like in the Gaussian world? Suppose we're in the Gaussian domain, okay, and one can still define monotone functions.
Sorry, let me just answer. That's an excellent question that I don't really know the answer for. It's a great question. It's possible that this would be one way to replace, but you see, we tried to apply analysis to this and this didn't work, and I think what you're suggesting is to apply this technique, replacement or addition to the environment principle.
I mean, I'm not so sure that the Gaussian question, like, again, I'm not sure what the question is, but that monotonicity testing, I think, okay, the monotonicity testing problem certainly becomes harder if the domain size changes from the Boolean hypercube to, let's say, the QAV hypercube for Q bigger than 2. It becomes a harder question.
Much harder to analyze, but I'm not sure that the values will get us so different, right? Maybe it is possible to even have the same theorem on a continuous domain.
Yeah, I mean, somehow, like, if one goes to the continuous world, hopefully there are tools of analysis one can do. I guess that's the whole point. But yeah, I'm not even sure what the right theorem is.
I'm not sure, but these are very interesting questions. We can say that we even deeply understand this inequality. This is kind of a surprising inequality to us as well. The fact that you can actually take the parallel here, and it is possible that you can apply either this inequality or similar ones on different domains and get some results out of it.
I had a quick question.
Hi, Adam.
Yeah, I was just wondering, you mentioned the open problem about adaptivity at the end.
Yeah.
For the, like, say that, you know, the classes of sort of lower bound instances that we have for the non-adaptive case, like this tiebreaker function you were mentioning earlier, is it obvious there how to get an adaptive tester that uses logarithmically many queries? Or?
No, we don't know. It is possible that square root of n is the right lower bound for adaptive as well, but it will require a lot of technical work.
No, but what about, like, just for, like, is it possible that we already have the hard instances, or at least, you know, for these specific family of instances, do we know that there's do we know of a better adaptive tester?
The simple answer is no, and the longer answer that I wish we had known better. We don't even know that these examples show anything about adaptive. It's interesting examples, but I don't know. As I said, we don't know a better tester. We don't know that having an adaptive tester helps at all. It is possible that the same lower one can be applied there, and in fact, so far we don't have any strategy of improving by using adaptive the tester. But what you're asking as well is what about this example of the tiebreaker, and I really don't know.
Adam, just for the simpler example, if you take just the anti-dictator, then you can do it in log n steps adaptively.
Just by binary.
Well, I'm not sure if you make it trivial, the same way that I did by trivializing the upper half and the lower half, I'm not sure that you still have this.
Yeah, I'm not sure I see how the end.
Well, if you ask a query that's half ones, half zeros, so it's in the middle layer, you'll be able to tell if a set of ones is in the anti-dictator or not. if the antidictator happens to be in a set of ones or not. So you get lots of information from that. I think you should be able to, after logging such queries, figure it out, no?
As I said, I'm not sure. Suppose you take the antidictator, but the same way that I did it in the slide, trivialize it by making all the inputs outside the middle layer being 1 above and 0.
No, I'm only asking the middle layer, so I'm only asking queries that are half ones, half zeros.
If you want it to be one-sided error, then you cannot make the difference between the two inputs larger than the square root of n, the same as I showed even in an adaptive case.
Well, okay, at least if I knew it's an antidictator, and I don't care, I just want to find it, that antidictator, I can probably do that using such queries. But, yeah, that's
if you can actually maintain the non-adaptive, the one-sidedness by actually checking even if you didn't find anything, maybe possible.
Yeah, I think Oded, you're basically explaining why this lower bound for two-sided testers of Chen et al. Is a non-trivial extension of the lower bound for one-sided testers. Right. So the argument you're giving is that in order to show a lower bound for two-sided testers, you have to come up with a family of instances that don't allow for the thing you were proposing, I think. So actually, maybe those lower bounds that come up for the two-sided testers are also, the instances that come up there are also an interesting place to look for, obstacles. I mean, either design principles or obstacles for adaptive testing.
So for the two-sided tester, the two-sided lower bound families are just half spaces. Like the monotone functions are half spaces with positive weights, and the non-monotone functions are half spaces with some of the constant fraction of the weights being negative. And I don't know. We probably felt at some point that for those half spaces, adaptivity can help in the sense of having log n queries should be sufficient. But this was never worked out for me. I mean, those instances seem like a bad candidate for proving adaptive lower bounds.
I believe we had a question from Praju, if it's still there.
Yes, I had a question. So it's like I want to understand the following: how does this isoparametric inequality that you prove feature in the tester? I mean, how can we exploit this isoparametric inequality and get the tester working?
Okay, let me just try to get. Okay, here is the important part where it comes in. So you see, this is the heart of the proof. This lemma here. You start with G minus, and then you're looking for G prime. And as I said at the end, what you're doing is going over all possible values for D, but still, you have to somehow prove that there exists such graph, and these values you just like try to set D appropriately. But the important part is here. See, we want to bound somehow this value here, sigma squared times D, to lower bound it by epsilon squared. This is exactly where the inequality comes in. You just apply it to all for D and say that at least one of them must be large in these terms. And you remember, you recall that in maybe something here is missing. Suppose what would happen if we take the square root of both sides of this inequality. So instead of sigma squared times D here, we'll have sigma times square root of D. And here we'll have epsilon. Now you see this is very similar to the inequality that we get in the isoparametric. I wish I could show them side by side, because over there we have the expected square root to negative sensitivity, which is really the square root of D. this is where it comes in. So I think I have to tie it better, but I hope this actually it helps.
So just to say it again, the isoperimetric inequality is used to prove the lemma, not in the step where you use the lemma to derive whatever we need about testing. It's just to prove that lemma, that G prime.
Indeed, I didn't have maybe enough time to show it, but once we've proven this lemma, the two techniques that I showed on how to resolve these two issues complete the proof. So the only remaining part is to show that there exists such a graph G prime. And I said there's some simple part that says let's try all possible Ds that are powers of 2. But then the inequality, the isoperimetric inequality comes in here to show that the value that we get, the size of the graph that we get is large enough in these terms. As I said before, you can think of this as being the number of edges times the number of vertices. And as you recall, I said that this type of isoperimetric inequality are in fact looking at both the edge boundary multiplied by the vertex boundary of the set. So this is really, I hope this actually makes sense of here, because we have sigma times d is the good, if you multiply by 2 to the n, is really the edge boundary, and sigma is the vertex boundary.
So somehow you're applying that isoperimetric inequality to G minus, but G minus is not a set. I mean, it's a graph, right? How do you apply it to G minus?
G minus, and look at all of the possible Ds that are power 2. For each one of them, look at all of the vertices in U whose degree is between D and twice D, and try it out. Then you get the logarithmic number of different graphs, and the isoperimetric inequality helps you show that one of them is large enough to satisfy this property here.
Thanks, that helps. Thank you.
Thank you. Okay.
Anita, do you want to say a few closing words before we?
Okay, so I should. Okay, so do we know how many speakers, how many audience, how many people were watching on YouTube?
Yeah. So we thanks also to everyone joining on YouTube. Yeah, there were about 6 more watching there, and I guess we'll see everyone in 2 weeks, and I'll take it offline. Everyone is welcome to stay and ask more questions if you wish. I'll just go offline now. Okay.